Okay, our next speaker is Dr. Elena De Momi, who is joining us remotely. Good morning, Elena.
Good afternoon.
Thank you.
Yes, thank you. Thank you for inviting me to this workshop, and sorry for not being here, being there.
Oh, next time.
Yeah, it's a strange time going on, so let's hope to meet soon in maybe in Migra.
Give us just a minute. We are setting up your presentation here on the big screen, so we can see it on Zoom, but we are setting it up for the people who are here in person.
Okay. Let me know just when you're ready so I can proceed. And I hope you can hear me well.
Yeah, no, the audio is coming across great.
Okay.
All right, I think we are ready to go. Well, are we? Okay. Yes. Okay. Dr. De Momi, I'll leave the floor to you.
Okay, thank you so much. And again, for the kind invitation and the congratulations for the workshop, which I've been attending since I woke up this morning. And it's really, really interesting. And the domain and the theme of the workshop is really hot nowadays. So in the line with the topic of the workshop, I build my presentation on the knowledge transfer between the expert and the robot in a medical application. In particular, my application is surgical domain. So let's say a brief recap where we are placing. So our research in the surgical domain, artificial intelligence has entered because we are basing our knowledge processing coming from the data that we can gather during the operation, and mainly the data that we are accessing are the images, because in our minimally invasive procedure, the endoscope is our sensory input, and we can process these images in an automatic way using computer vision methodologies and machine learning, and we gather knowledge about the situation that we are coping with. In the meantime, we can also include the previous knowledge of the expert. For example, the knowledge about the surgical steps, the knowledge about the surgical instruments to be used, and so on. So and so forth, we can also change the control methodologies according to the surgical step that we are coping with. The loop has to be closed with explainable artificial intelligence. As the previous talk was pointing out the importance of explaining the results that we achieved using black box models. The knowledge represented by the expert with the top-down approach can also be used to interpret the results that our classification methods give us automatically. Why do we need this automatic reasoning, automatic process of decision-making? The parallelism with the automotive industry is clear. So we are accepting autonomy in driving because we want to increase the safety of driving, and so we want to avoid risky situation. In the same way, we are increasing the autonomy of our surgical system because we want to increase patient safety, we want to reduce the errors, so we want to have an overlay, a sensory overlay, which gives some information which we cannot detect immediately with open eye. And the path has been tracked. So this interesting paper that has been recently published classifies the same level of autonomy as in cars industry, and it gives an immediate picture that in the future, the level of autonomy is going to increase and more application will be embedded with autonomy artificial intelligence. And the certification process has also adapted, because this is a picture of in several years, so starting from 2016 till nowadays, the number of devices that have been granted the FDA approval in the different ways so that the FDA approval can be achieved, embedded with artificial intelligence is increasing. And there is also this database about all the devices embedding artificial intelligence that have been granted the approval. So the process is happening. It's gonna raise in the future, and it's also put in the market thanks to the approval that you can get. In the same way, in Europe, since a few years, we've been reasoning about the artificial intelligence. There is this interesting document provided by the European Commission about the ethics guidelines for trustworthy artificial intelligence. Trustworthy means that it has to be reliable, robust, and our ingredient is to have the human in the loop. So there should always be a human agent oversight in the process of learning. So let's come to the, let's say, core of my talk after this introduction. So the idea of our research recently has been to transfer the knowledge from the expert to the robot in order to have an autonomous system able to cope with the uncertainty of the surgical field. In order to do that, we do this with having a knowledge transfer, but also transfer learning, because everything can also be represented in a simulated environment and then be applied in a realistic simulated environment and then applied to the surgical cases. So the talk will be structuring with three main moments. The first one is the augmented reality, which can be on which we can leverage to increase the knowledge transfer, and then two use cases, one applied to neurosurgery, the other one applied to cardiovascular surgery. So why augmented reality in the knowledge transfer? Because, for example, in this case, we have a complex task. Was just actually the surgical task was simple, was just to follow this line on the surgical phantom. The complication here is that we have a constraint on the robot motion, which is this remote center of motion. So the trocar ports in which the robot should pass in order to reach the phantom organs. After a complex calibration procedure between the robot, the augmented reality devices, so the HoloLens, and the surgical pointer, we were able to provide two mechanisms of teaching. So the first one is traditional hands-on teaching, so kinesthetic teaching, while the user is guiding the robot in hands-on control in order to perform the desired trajectory. And in augmented reality procedure, the surgeon is able to virtually guide the robot. The user is seeing this virtual hologram of the robot on the surgical scene, but the user is also aware of the constraint, the further constraint that the robot should respect, so the remote center of motion. So this is a sort of a closed loop mechanism in the teaching phase, in which the user is also able to see in real time what the robot is learning and how to correct the robot approach towards the application that is gonna learn. So these are the preliminary results that we have been achieving on this. So this is simple surgical task with a constraint that has to be taught as well to the robot. And the preliminary results show that are promising, in the sense that with respect to the traditional learning by demonstration, the results are improving. Still, some further work has to be implemented, of course. So let's switch to the two use cases in which we are applying this knowledge transfer between the expert and the robot. In both cases, we are addressing steerable catheters, and in the previous presentation, we also applied the concept of reinforcement learning. Actually, we are switching to inverse reinforcement learning. Why? Because we want to not just give to the robot some rules to behave in the surgical environment, but also taking example from the expert. So the approach is kind of reversed. The environment is still acting on the agent, but the rewards are not only coded a priori, but we are also including the expert knowledge in the domain. So this is the first case I'm presenting. It's a European project that we have been part of from 2016, and the case was to address a tumor region within the brain to provide drug delivery, enhanced drug delivery to the tumor region. So the environment is complex. We have to avoid some structures like the ventricles. We have to avoid all the vessel. We have the possibility of selecting different entry points, and we have to reach the tumor with the precise pose of our steerable catheter. And the problem was formulated in inverse reinforcement learning. The agent is the steerable catheter, which has some degrees of freedom. some curvature constraints, and can perform some possible actions in the environment. As said, the reward was to achieve the target pose, to avoid the structures to be avoided, to respect the catheter kinematic constraint, and to get the minimum path length. So this was and the expert demonstration. So this is the input that we are adding. The expert is manipulating a joystick in a simulated environment and is selecting desired path as you interacting with the simulated system. So as it's done here in this picture. So this is the point of view of the expert navigating through the complex environment. From the simulation environment, we went to the real case, mimicking the brain tissue with some gelatin material, and we are able to get some good results in terms of computational time to get to the target and targeting accuracy. The expert knowledge was also translated in terms of rules. So the rules enter also into play in our targeting path, in our path planning mechanism, in terms of constraints, which helped in defining the best entry point. So the path planning was left to the inverse reinforcement learning, but the selection of the entry point was left to some pre-coded rules gained from interviewing surgeons, neurosurgeons about the preference on the entry point. And again, we got good results. The last part is how to achieve transfer learning. So we can simulate, we can train our system using a simulated environment, which have to be realistic. So in this case, for example, the dynamic environment has been simulated using particle systems, which take into account the dynamics of the system. And and you can see here that also from experimental data, while the catheter has been inserted, you have a deformation field around the catheter. So this can also apply some unwanted displacement to the catheter while being inserted, but this can be corrected as said. They can be compensated with, let's say, with further training of the algorithm. So this is the final setup that we managed to achieve. We performed some tests on some sheep, and this is the integrated system which was brought to the veterinary lab in order to perform our final test. So in the interest of time, and I'm skipping to the last application, still we want to have a curvilinear catheter. Now it's implanting the mitral valve through this femoral axis. So it's a catheter climbing to the vessel and climbing to the heart, perforating the septum and reaching the atrium in which we have to implant this mitral valve. The same, so we are actuating the system. So we are working either on the actuation system and this is the final steerable part of the catheter. It's a commercial system, but it's as it's on the market now, it's manually driven. So the process is really complicated to manually actuate this mitral clip device to land properly on the mitral valve plane. So again, we already actuated the system, and now we have to compute the best plan, the best path. And again, we are exploiting this inverse reinforcement learning paradigm, taking in expert demonstrations, generalizing the trajectory to our case. And this is what we have been achieved so far, and this is still ongoing work. This is another European project that we are leading in Politecnico, and but still going on. So we have 2 years in front of us to integrate the system also with the other partners in the consortium. So just to recap what we have been doing, transferring the knowledge and also training the system on simulated data, but being able then to transfer in real application, as I showed you before, on gelatin, but also on our animal example, so in vivo animals that we in which we explored the possibility of implanting this steerable electrode Eden. So just to try to give an answer, so there is not an easy answer to the question posed by the robot, by the workshop, but of course transferring, so making robots learn has some risk because it depends. We are generating a cognitive bias according to the users that we are interviewing and to the user who are teaching to the robot. In our case, we use some neurosurgeons who belong to the same hospital, and we are doing the same with the cardiovascular approach. And you have, so having this cognitive bias can, of course, generate some problems in the possible certification process. But we have some benefits for sure. We can standardize the process because we are getting knowledge from the expert, and we can easily transfer this knowledge to, let's say, other settings in which you don't have that expertise. And we are seeing this, for example, in the training. So when we were interviewing our surgeons in order to perform the expert-based trajectories, for example, this became quite clear that it was easy to transfer this knowledge in a simulator, which can be used to train a non-expert surgeon. So this is some certain benefit of this process. And of course, you are increasing the safety of the procedure, which is our final goal. It's, as I said, it should be a human-centered approach, and we have to understand how much is the percentage of the human left control and how much is the system able to be autonomous. Thank you for your attention. And I'm open for questions.
Impressive work. Thank you so much for sharing it with us. Are there any questions from the audience? Either in person or virtual or in spirit? Yes.
Hi, thank you for your talk. The inverse reinforcement learning, this sort of reminds me of imitation learning. And I know a problem with imitation learning is that I guess you can't really outperform what the expert advice you're learning from. So could you explain to me how inverse reinforcement learning is different to imitation learning?
Thank you for your question. It's really, really interesting. So actually in our approach, we are just slightly modifying the inverse reinforcement learning approach because we are still using the rules. So let's say the punishment and the reward functions and the punishment given on the basis of the desired performance of the catheter. So we have, let's say, general constraints that we are applying. So you have to respect the kinematic constraints. You have to get to the target, to that particular orientation and position, and you have to stay away from obstacles. So this is general knowledge that we are applying to the system in the forms of rules. But then we are also combining this, let's say, pre-known knowledge with the expert trajectory that you should imitate. But let's say, from the expert rules, you need to generalize. So you can apply some, for example, some interpolation methodologies from the trajectory given by the expert in order to, let's say, don't stuck to that particular expert trajectory, but try to understand the desired behavior that the expert is teaching. So it's a combination of the two approaches, I would say, and I think that this could be a solution to possibly get stuck in the, let's say, imitation of just what the expert is telling you to do. I don't know if I answered to your question.
I think that makes sense. Thank you.
Thank you.
Okay, we have one more question.
Hi, thank you for an interesting talk. I wanted to follow up on the topic of learning from the expert. So as this will scale, I imagine you would like to involve more cardiologists from multiple centers. So there I would expect some variance in the techniques and how they handle their instruments. How do you see that progressing towards the future? How do you want to distill that information and have the robot do as the cardiologist does procedures?
So the MitraClip procedure, for example, the second one in my approach is really, really a complicated procedure. And there are some a small number of experts who can perform the approach. And there are a lot of courses in which such experts teach the others how to perform this complex maneuver that you have to make on the handle in order to properly land on the mitral valve plane. So I think that what we could do, for example, an idea could be to participate to one of these courses that they make on how to teach properly to use the system and to gather knowledge from them. Of course, we should, before, let's say, translating this knowledge to the robot, we should analyze and classify, maybe clustering the expert performances before giving them to the robot in order to see variability, for example, and also try to associate the expert maneuver to the performance that you achieve. Because maybe in some cases you don't detect there are some biases or some drawbacks in how the procedure is performed.
So in terms of performance, then you would look at the actual surgical outcome afterwards?
Well, no, in these training courses, they are using, I think that they're using phantoms. At maximum, they are using its animals. So we don't wait until the surgical outcome, which can be, let's say, let's say cardiac response after 1 year. I think that in order to translate these expertise to the system, we just based on what the surgeon is, let's say, judging as a good implant on the images that you have on the phantoms on the animals.
Okay, clear. Thank you.
All right, please, let's thank our speaker once again.
Thank you again for your attention and for inviting me.